So we will have a final examination, which is really just another midterm, and that will be on Thursday at our normal time. We'll have an hour and 20. It'll be 50 questions in length. It will be identical in structure to the first midterm. The question formats, its style, everything will be quite similar. The only thing that will change will be the subject material. So instead of ecology, you're looking at evolution, but besides that, should not be any surprises. Are there any general questions about it in terms of structure and format? All right, so when you guys come in, just make sure that you sit quickly. We'll hand out exams as rapidly as we can. Make sure to bring a number 2 pencil. We'll supply the Scantron forms and the examination. All right? Okay, so today I want to talk about reproductive isolation, which is the 4th step in the microevolutionary process. And I also want to do some brief review. So I think we finished up talking about we started last time with artificial selection, is that correct? So what's the difference between well, before I do that, I think we talked about why, can you create a perfect organism via evolution? No. Would you want to? No. Why would you not even want to do that? Yeah, because once you're perfectly adapted to a set of environmental conditions, the conditions will change and you'll go extinct. So it's not the best idea. All right. So I gave you a series of rationale as to why evolution does not create a perfect organism, right? And so what are the 4 reasons that you don't create perfect organisms via evolution? Number 1, you can only select for what? Things that already exist. And the things that already exist had to come from someplace before in the past. And then finally, adaptations are often what? Compromises. It'd be great to have wings and 4 legs, but it doesn't work that way. I've got to give up a set of legs to develop into wings. So there's always adaptations and they're always compromised. And then the last one is the most important probably of all, which is simply what always interferes. Chance events happen all the time to basically select out the best variants just by chance alone. And that creates better than conditions. And that's really how evolution works. It's better than this. It's better than that. That's all. It's not perfect. We started talking about genetic divergence. And so I gave you 2 basic ideas. If alleles are coming into and out of a population, what is that? That's gene flow. What does gene flow do to the overall variation in the large global population? It increases the overall amount of variation, but what does it do between the differences between subpopulations? It homogenizes them. Very good. Genetic drift does exactly the opposite, right? What does it do to the overall allele composition of the global community? It typically does what? It decreases it. But what does it do to the differences between the subpopulations? It increases them. Okay? So it does exactly the opposite thing. Gene flow brings more in globally, but overall the differences between subpopulations are decreased because you're more homogeneous. Genetic drift is exactly the opposite, right? What it's doing is decreasing the overall allele composition of the global population, but it's actually increasing the genetic differences between the subpopulations. The smaller the population, what happens to the effect of genetic drift? It goes up. So the smaller the population is, the bigger the effects of genetic drift will be. Often, what is that effect in terms of alleles? What will it have a tendency to do?
Fix for one.
It'll fix for one or completely eliminate another, right? Once it fixes for one, it eliminates the other. And that leads to homogeneous condition in the population. Is that a good thing?
No.
No, because again, I have less arsenal against environmental change, and that's a problem, okay? So I gave you 2 conditions which could actually enhance the impact of genetic drift by shrinking the overall population size. The first one was when you had some kind of disruptive event that really shrinks the overall population size down, and the ones that get through that little constriction are not representative of the initial population in terms of allelic composition. It's usually reduced. What's that called? That's the bottleneck effect, right? You can rebound in terms of numbers of individuals, but what's the problem?
It's the only curve is there.
There's not as much allelic combinations left, right? It's not as diverse as it was before. You can basically create new diversity, but it's going to take time. How do you get new diversity in the alleles in that population? Mutation, gene flow, and natural selection can also kick in different ways. So there's ways to basically get it back, but it's going to take some time, right? What was a nice example of this? The seals and the cheetah. So the expectancy, how would I ask a question like this on examination? What do you think is the most likely way you'd get something like this? Am I going to ask for a definition? No. What would I do? I'd give you an example. That's exactly right. I'd give you some example. Organism X underwent a period of reduction in the population size due to a hurricane. The population that was left had less genetic variation. All right, I can start it in a different way. I can say there was 15 colors of lizards before the tropical hurricane hit. Afterwards, there were 2 colors of lizards left. What would this be an example? Something like that, right? So I can come up with an example that would basically describe the phenomenon, and I'd expect you to match it. That's how, just like the ecology examination, that's what I expect you to do. Take what you know, apply it to an example, a problem, and solve it, okay? All right, a similar effect, but a very different mechanism. In this case, instead of a disruptive event shrinking the overall population size like a disease or something like that, in this case, you just get a subset that decide to migrate away. What's that referred to as? The founder's effect. You notice the migrants have a smaller subset of the allelic frequency of the original population, and therefore it's typically less diverse. Again, it can rebound in size. Will it ever look identical to the original population? Never. Why not? Wherever it went, what's the difference? Why won't I have exactly the same allelic composition? Ever. Because the new environment is what? It's different than the old environment. It's never going to be exactly the same. There's always going to be subtle differences there. And again, I only get to work with what I have. So basically, there's that historical constraint. Mutations will kick in different ways. Natural selection will work in different ways, and chance will work in different ways. It may become quite robust again in terms of its variation genetically, but it's never going to be exactly the same. I could get it to be exactly the same if what happened? What would be an exception to that rule I just gave you? What's the only thing that could homogenize the differences? What is it? Gene flow. If gene flow was excessive, and there was quite a bit of it between the old population and the new, I could recalibrate and bring all those genes back in. This is the nice advantage of a founder's effect versus a bottleneck effect. Because in the bottleneck effect, what's the problem? What happened to all those old alleles?
They're gone.
They're gone. They're dead. But in a founder's effect, they're still there someplace. And if migration routes opened up between the two populations, I could actually homogenize them again if there was enough transmission of alleles between the two populations. That would be an exception to the generalization. All right, we talked about how you get the formation of a daughter species from parental species through genetic divergence. Remember, any kind of physical barrier can enhance this and stabilize it quite quickly. I gave you a nice example of genetic divergence in the birds. Do you remember what they were? They were the meadowlark. Remember the western and the eastern? What was the only difference? Morphologically, they were identical. Their song was different because they had been cut off by the Rocky Mountains, okay? So again, genetic divergence is going to lead to differences in the gene pools of the daughter and the parental population, and then it will quickly diverge. Mutation, natural selection, genetic drift, all kicks in to separate them further. All right, that brings us up to today. And so let's kind of run through our little mantra with the microevolutionary process. So variation is acted upon by natural selection, which leads to genetic divergence, which can supported by reproductive isolation, which can lead to speciation. Very good. Now this is a great study technique for yourself because you can think about it as a flow chart. Remember I gave you those flow charts for ecology? You can do the same thing with this flow chart, just add in the pieces. So basically you start off with variation. Well, what are my additions to that again going to be? They're going to be, what are the sources of variation? What are they? Mutation and recombination. Which one's the primary? Mutation because it creates new alleles. Is recombination not important? No, it's very important, but it just does what? Reshuffles the deck. Okay? And then you can work your way through those. Talk about the different types of mutations. What are they? Chromosomal and point mutations. Very good. We talk about the types of variation. What are they? Continuous, polymorphic, and ecogeographic. Now that's an easy flow chart to remember, right? That covers the first part of variation. The thing is, now you have to know about the examples, and if examples were given, could you basically recognize them? Then you work your way down the list. What's second in line? Variation interacted upon by? Natural selection. What are the three modes of natural selection? Stabilizing, directional, and disruptive. For each of those, you should know what are the assumptions in terms of environmental conditions, right? What would the graphical representation of it look like? And if given an example, could you identify it? That's the way I would test on it. Natural selection leads to genetic divergence. So in genetic divergence, what did we talk about? I talked about two primary mechanisms here. One is homogenizing the population. What is that? Gene flow. One is diverging it further. What is that? Genetic drift. And genetic drift has two components to it, which we've talked about, which is one where it migrates away, founder's effect, and one where you have disruptive event, which is the bottleneck effect. And then you should have examples of those. So that's how I would logically and scientifically study for an exam like this, right? I would walk through that flow chart, know all the basic information about it, and then be able to express examples of it. Now, we haven't spent a great amount of time on computation sets, but they're going to be on there, right? So I haven't been putting them on lecture because the lectures are pretty thick, and I didn't want to gunk it up too much with it. But the TA's been going over them with you, so you should know those. How do I know if a population's evolving for any particular trait? I need to have a baseline. How do I run that? Hardy-Weinberg equilibrium, okay? I need to know allelic composition in any particular population. How do I do that? Allelic frequencies and being able to calculate that. If I want to know if it's Bally polymorphism, I should be able to run a Punnett square to basically analyze that as well. Okay, so now we're brought up to speed. Now we're just looking at the last piece here, which is genetic divergence is supported by reproductive isolation. That's what we want to spend some time talking about today. Again, am I giving you all of evolution here? No, because I'm leaving out what? About 85% of the world, which is organisms that are not sexually reproducing but doing what? Asexually reproducing, okay? All right. So let's talk about that.
Oh, man.
That doesn't look good. Why is that just dead? So that means that there's not a center camera, so that means it's twisted physically, right? Yeah. So maybe if I use the other camera, it would be okay? How do I do that, Doug? Let's see. Let's try stage left.
Rip.
Oh. Like that, didn't they? All right. We'll make it work.
Oh.
Yes. Yeah, that'd be great.
Oh, there's two.
Now they're both on, huh? projectors off from up there? Is it possible to manually turn a projector off?
Yeah.
Could you turn off the right one? There we go. Well, nice to have a tech at the room. Thank you. Sweet. Thank you. That's like one of those computer nerd moments where it's like, move. I'll take care of it. That's how I feel with my grass feed sometimes. It's like, just move. Okay. There you go. I'll type all in for everything. All right. Now when I say that, it's them telling me to move, not the other way around. Okay, so let's talk about reproductive isolation. So, when you think about reproductive isolation, we're talking about any kind of empirical change in your morphology, your physiology, or your behavior that prevents interbreeding between the divergent group and the original parental group. Well, that's going to cause a reproductive separation between those two groups. You can no longer reproduce. So we can code this as an RIM, it's a reproductive isolating mechanism. And it's a byproduct of genetic divergence. As you genetically diverge, often this is the outcome, is reproductive isolation. It's not kind of the end goal, it just happens to happen that way, all right? But it ends up actually being quite beneficial to most diverging populations, and this is why. When you migrate into a new habitat type, are the conditions environmentally ever going to be the same as they were before? They're not. So typically, adaptations for that particular environment will be quite different than they were from the precursor environment. So as those adaptations begin to accumulate and new allelic combinations arise to deal with it, would I actually want to homogenize my population with alleles from the whole population? I wouldn't, because those alleles are specialized for that environment, not this environment. Does that make sense? So isolation, in a sense, can be quite good because it speeds up the pace of evolutionary change for particular environments. So a reproductive isolating mechanism will maintain the positive adaptations for very specific environments, and that's why it's quite a beneficial thing, typically. There are two types of reproductive isolating mechanisms. The first one is a pre-zygotic isolating mechanism. The second is a post-zygotic isolating mechanism. Obviously, excuse me, and the first one is occurring before zygote formation. The other one is occurring after zygote formation. When you take a look at them in terms of their severity, what you typically see, and this is a generalization, but most of the time it takes place, is the post-zygotic isolating mechanisms have a tendency to be much tougher to breach than do the pre. So kind of if there's a will, there's a way to breach the pre-zygotic isolating mechanism before fertilization. But once you've fertilized, there's some really strong ones that kick in to basically prevent the successful reproduction between two different species and between a parental group and a daughter group in terms of evolutionary descent. So let's take a look at some of these. So let's start with the pre-zygotic isolating mechanisms. And a very common one is ecological isolation. This is real common. So it's basically isolating reproduction between two groups based on the ecology, either biological, abiotic in nature. So a nice example of this would be these oak trees. So these are really common here along the south coast. And as you make your way from kind of the lowland coastal areas that go up the mountainside to the top, you will see a transition in the species of oak tree that you find. So down at the bottom, you have this Quercus lobata, and that's the valley oak. It's a large tree, it spreads out really wide, the leaves are relatively large and thin, they have a lot of surface area to them. As you make your way up kind of the foothill areas, you start to see the live oak, which is really typical of this area. Unfortunately, a lot of that's been cut down via development, which is a real shame because it's a beautiful tree. If you go kind of north a little bit into the San Ynez area, see them everywhere, the Lompoc area on the way up there, you'll see them all over the place. And this is Quercus agrifolia, and it's the live oak. It's the one that has all the gnarled trunk shapes and all that to it. When you look at the leaf, it's a smaller leaf, it's thicker, it has more volume and less surface area. And then as you go right to the top of the slope lines on the mountainside, you'll see Quercus dumosa. Quercus dumosa is known as the shrub oak. It's a much smaller tree. And when you look at its leaf shape, it is very volume rich, but surface area poor. So it's a very thick leaf, but not a very wide leaf. Okay, it's quite small in terms of surface area. And so each one of these trees, they're related to each other in terms of evolutionary descent, but there's very little breeding between them. There are some hybrid zones as you make your way up the hillside where you can find a blend of both trees. But here's the issue. If I'm Quercus lobata, would I actually want to interbreed with Quercus dumosa? Is it beneficial to my population to do that? It is not, because are the environmental conditions the same from the bottom here at the coast to the very top of the hillside? They're not. What's changing as you go from the bottom to the top? Humidity's changing. What else? Temperature's changing, and what else? Water amount is changing drastically. Where's there more water, at the top or the bottom? Much more water at the bottom. So our rain season here is quite seasonal. It only rains a couple months out of the year, and then that rain doesn't last very long. All the rain that falls eventually makes its way down the slope sides into rivers and then out to the ocean. Okay? So there's much more water down here, and the soils are thicker. As you get towards the top of the mountain, the soils are very rocky. Topsoil layer is very, very thin. So if I'm at the bottom, these are primary producers. What is their goal here? What do they want to do? They want to make their own food, and they want to grow, and how do they do that? They convert light energy via photosynthesis into a usable food, which is glucose. That's exactly right. So if I'm down here at the bottom and I want to make as much glucose as possible, do I want to increase or decrease my surface area of the leaf? I want to increase the surface area of the leaf, but there's a problem that happens when you do that. Yeah, I'll generate more photosynthesis, and therefore I'll generate more glucose as a photosynthetic product. However, I have to give up a lot to do it. What do I give up? Water. So remember, what is the photosynthetic equation? CO2 plus? CO2 plus? What's the other substrate? Water. Thank you. CO2 plus water, hit it with light, gives you oxygen as a waste product, glucose as your primary metabolic product that you're going to consume. C6H12O6, right? But you have to have water to do it. Not only that, but how do you cool yourself down if you're a plant? Can you just sweat? You can't sweat, but you can do something that's analogous to that, which is to what? How do they cool themselves down? If you get cool, you can sweat, but you can also do what? You just sit in the sun and go, God, I'm hot. I'm just going to sit here and sweat. What do? You go in the shade. That's exactly. You move. Get the hell out of there. Go sit in the shade. Can a plant do that? Plant stuff. Doesn't have many options. So its only option is to cool itself down metabolically. Well, how does it do it? Why does sweat make you feel cooler?
Evaporation.
As it goes from a liquid to a gas, what does it liberate? Heat. That's exactly right. And plants can do exactly the same thing. They can convert liquid water into a gas and liberate the heat from their internal surfaces. And therefore, they cool themselves down. But you have to have a lot of water to do that. So if I have a big, wide leaf that's real thin, I can do a lot of photosynthetic work, but I'm going to give up a lot of what? Water. Well, if I'm down at the bottom, can I get away with that? Yes, because there's a lot of water down here. But as I make my way up the hillside, the water starts to decrease in its availability, and the conditions start to get harsher because they start to get hotter and they start to get drier. Okay? So what happens is the leaf shape has to change, and so does the size of the plant, because I can't pack on as much energy. So what's happening to the leaf? The surface area is doing what as you get to the top? It's getting smaller and smaller, but the volume is doing what? It's getting bigger and bigger. That helps them retain their moisture, not dry out. It also makes them much more resistant to fires. Where there's more fires, at the top or at the bottom? Always at the top than at the bottom, okay? So it's giving them a couple advantages. So here's the thing. Do I want to have small leaves if I'm down at the bottom? No. I don't. And if I breed with that, I'm going to get smaller leaves. Do I want to have big leaves from at the top? No. I don't, because I'm going to dry out and I'll burn more. So mating between these is no good. Mating between any of them is no good. So what you typically see is a resistance to that mating and a segregation based on their ecological niches. There is some hybridization, but it's very narrow bands, and the hybrids don't do very well, okay? They're prone to the tendencies of their environment to exclude them. So that would be a nice example of a physiological mechanism, which is water retention, to promote basically this diversification, this reproductive isolation between the groups. Here's another one, geographic isolation, super common form of prezygotic isolating mechanism. In this case, you're isolated, the daughter and the parental group are isolated due to some geographic barrier or distance. They don't come in contact with you, completely relative to the size and the motility of an organism, right? So we've talked about this before. Human being on one side of the Rockies, human being on the other, no technology, easy to surmount? Pretty darn difficult. Birds? Easier, because now I can fly through the gaps at certain times of the year. So, again, bacteria in this seat versus bacteria in this seat, universe apart, unless something moves them between the seats, okay? So here's a nice example. This is actually body lice, all right? So this is lice. Maybe as a kid, how many of you guys had lice? Raise your hands high. Yeah, it's quite common, especially in things like nursery schools and kindergartens. Has anyone ever been to a nursery school or kindergarten before and watched it? It's like barbaric, yes? And so, they're sticking each other's fingers and eyeballs and mouths, and it's just gross. And so you transmit all kinds of stuff all over the place. And so disease spreads quickly, and lots of parasites and lots of things like this will transmit as well. So when you take a look at lice, there's actually two subspecies of lice. There's the head lice. There's an example of someone on someone's scalp right there. Okay, there's a lice. And so that's called Pedunculus humanus variety capitis. So the capitis refers to the head. The second subspecies is body lice. Now body lice is Pedunculus humanus variety vestimentae. Vestimentae meaning body covering, okay, the vestment. And so there are two species, and they're quite subspecies, and they're quite distinct. They don't breed with each other, but they can. So morphologically, there's no problem with the breeding, but they don't breed with each other because of geographic isolation, right? Separation that prevents the mating. So think about this on the body. You have body lice. Where are body lice found typically on the body? If you're a man, where are they found? The back, the chest, and the groin. And if you're females, they're typically found where? In the groin. And then head lice is found on top of the head. So for females, it's pretty easy to see where the geographic separation is, right? Because there's a big area without a lot of body hair on it. For men, it's less so, and men have a lot more hybridization of the species than do women. But there is one place on the human body that really acts as a geographic barrier for lice to move across. And they won't move across the area. So if I'm a lice, why do I not move from the head to the body? Why not just make the trip? I'm small. Why don't I just make the transition? Why don't I go from the head to the body? Why don't I cross an area of relatively hairless body? Not that, so that you feel it, but you'd what? You could see it. That's it, right? They're hiding in the hair, so you can't see them when they're in there. But if they have to go across an open space, they can get caught. And so they don't like to make that, right? First, the movement, you can sense it in some cases, but it's the sensing of the movement, and it's also the sight that they're really worried about. So they don't cross those gaps. You see the same thing for lots of organisms. I teach a tropical ecology course, and one of the case studies we give is when you fragment the forest, certain kinds of monkeys won't make the crossing, right? The wider the gap gets between the forest, the less they are likely they are to cross the gap because they get seen and they can get captured. So this is what happens here. Now, where is the big geographic barrier on the human body, even for men, where they will not cross? Do you know where it is? It's not the neck, because actually the neck for men is quite hairy. They shave it, right? Well, there's lots of men with hairy backs. I've seen them before. They're there. That's like a nice superhighway, right? Up and down. There's another place. Where's the barrier? It's above the chest and below the neck. It's right where the collarbone is. So that's actually the place on a human being that has the less hair than anywhere else on the body except for the palms of the hands and the feet. So it's right here. There's a barrier that they won't cross. What's interesting is depending on the human being and their degree of hair, you can get more hybridization. So for instance, if you're really hairy and you have like hair that goes from the back of your head all the way down to your butt, across your back or something like that, hybrids will just travel up and down that. It's the lice superhighway, right? Up and down they go, there's no problem. But if you have divergent zones, then they won't travel. Here's an interesting thing. You know that IV has one of the highest rates of body lice in the county, yes?
Wait. That's what I like
It does.
to do.
So it's kind of interesting. It's found in the children, and then it's found in the college age. It shifts though. It goes from head lice to body lice, which was commonly called what? Crabs. That's exactly right. And so there's lots of different ways to catch crabs. Obviously, the first way is what? Sexual contact. He says that very. Sex. What's the second way? It's roommates and it's sharing clothes. That's exactly right. Not washing clothes consistently and sharing clothes. There's another way you can catch them, which is actually more common than you might think it is. Any idea? Not necessarily, usually pets, because they're species specific, okay? But it's actually, can you see this picture right here? That is lice on furniture.
No.
So lice can exist for extended periods of time in furniture upholstery and wait it out until someone else happens to sit there. Did any of you guys inherit a couch from IV? Moved it to your apartment? Raise your hands if you did that. Yeah, probably not the best idea. So you might want to fumigate that couch. Because if you had a roommate that had body lice and decided to lounge on that couch for extended periods of time, they may just be waiting for you as the next host. So that's a really nice example of geographic isolation. You're all like, I'm going home.